Section 5.2 is multiplication and division of integers. We're going to see a couple models that we have seen before, the charged fields model, the CHIPS model, the number line model, so 3 models that we've actually seen before, to talk about how multiplication specifically works. And we're going to start in with the CHIP model. All right, so I'm doing an example that has 2 negatives because I think that we've very well covered what happens when you multiply positive numbers together, right? When you have positive times a positive, we can put things in an array. You can make an area image, something like that. So we're going to see what happens with the CHIP model when we have 2 negative numbers. All right, so draw yourself a circle. That's a really thick one. Let me try this again. That'll work. And we're going to write a little bit of language next to the -4 and the -3. So the language I'm going to put next to the first one is that the negative in front means to remove, and the 4 is going to say to remove 4 groups. And then my -3 is of 3 negatives. We're going to remove 4 groups of 3 negatives. Now, we start out with nothing in our circle. There's nothing in there. Okay, it's worth nothing right now. And we're going to put things in that allow us to remove 4 groups of 3 negatives. But I can't just put things into a circle. The one that we did on the board here, I think Veronica asked us about this one. In order to actually start, I started with a -2, and I wanted to have 3 negatives to remove. I had to insert 0 pairs, right? If I inserted a positive and a negative at the same time, or a black chip and a red chip at the same time, it kept the circle's value, whatever it was before. And the same is true for this. So we're going to insert positives and negatives at the same time. This is the chip model, so we're going to use our positive and negative with our red and our black chips. And I'm going to insert pairs of chips. For every black chip, there's a red chip. So what's the value right now inside my circle? It's 0. I've got an equal number of red and black chips. They cancel each other out in terms of their value. The number inside my circle, the value is 0. But the cool thing is I now have the ability, and if I put too many things in here too, I could take them out later. It wouldn't hurt anything. But I have the ability, because we know that 4 times 3 is 12, we have the ability now to remove the 4 groups of 3 negatives. So I'm going to make a group of 3 negatives, and I'm going to remove them. And I've done it once now, twice, 3 times, and 4 times. And in doing so, what do I now have left? What do I have? 12 positives. That's what's left inside my circle. After I have removed the 4 groups of 3 negatives, I have 12 left inside my circle. Hence, a negative times a negative equals a positive, in this case a positive 12. Now we can do the same sort of thing with the charged fields model, of course. So if we draw our circle, we can write 0 pairs with positives and negatives.
How would the kids know how many to draw in there?
Well, remember at the point when you're teaching this, kids know how to multiply because this is probably about 5th grade. So they're going to know that they have 4 times 3 is 12, that they're going to need 12 in there. That's how they would know. And the reality is that the process that we're doing it for small numbers because the idea is to give us a visual picture of what's happening. But you're not going to do this for 42 times 37, right? I mean, we're not going to keep doing this forever. This is not an efficient process. It's supposed to help you understand, in part at least, why a negative times a negative is a positive, or why a negative times a positive is a negative, that kind of thing. We're able then to remove 4 groups of 3 negatives. And we end up with 12 positives left. Those are some sloppy positives, aren't they? All right. You guys ready to check out the number line model? All right, we're going to write a little bit language too associated with this so that when you look back at this, you'll be like, what was I thinking? Because it's really hard to draw this. It's easier to do it because I'm going to actually like stand up and walk the desks for you like I did last time. But let me show you what happens when we do this one on paper first. Okay, the first -4 is to move 4 left. I'm sorry, move left. Let me change the order of that. Move left 4 at a time. So kind of like skip counting. You guys know what skip counting is, right? Skip counting is when you skip certain numbers. So like if you go 2, 4, 6, 8, that's skip counting by 2s. We're just going to do it going left. So we're going to go 8, 6, 4, 2, going backwards. That's skip counting by 2s. This is doing it by 4s. And then the 3 says, and this is the awkward part. I'm not a fan of this. I'm just going to tell you right now, I'm not a fan of this. This says the time starting 3. We're going to use the word hours. There's no reason that it has to be hours, but it's 3 units of time ago. So I'm going to draw the picture, okay? And then I'm going to actually make the steps in front of the class. So draw your number line. And you're going to be moving left, so we're going to be starting on the right. You don't necessarily need to mark what value you're starting at. Just mark it. And you're going to move 4 at a time. So here's 1, 2, 3, 4. So here's my jump backward 4. 1, 2, 3, 4. And here's my jump backward 4. And 1, 2, 3, 4. And here's my jump backward 4. And the reason I did it 3 times is because I'm multiplying by -3. 0 is where I end. So thinking in terms of a number line, where did I begin? 12. And where I began is my answer. So actually, I don't even think I'm going to do this. There's an example. There's an example in your group work. We're not going to get to it, so let me just talk to you about it because I think it does a better job even than the physical movement of describing this process. It talks about an example of a school. I think it's a school losing enrollment. The enrollment numbers are going down in a school. So you've got a high school. They're losing enrollment for whatever reason, and they're losing the enrollment 50 persons a year. So 50 kids a year are coming, fewer than the year before. And it talks about this happening for 3 years in a row, or 4 years in a row, whatever the number is. We'll say 4 years in a row. So for 4 years in a row, we lose 50 kids each year. And the question asks, how many more kids did we have at the beginning than we do now? And the answer would be 200, because we had lost 50 kids a year for 4 years in a row. So you're starting back at what did I have at the beginning? What did I used to have? Something that's decreasing consistently over time, and what did I used to have? And that would be a good example of this sort of visual imagery of what's happening on the number line model. Okay? All right, a few facts about integer multiplication. A and B are integers, and if A is negative and B is negative, then AB, multiply them together, is the same thing as the absolute value of A times the absolute value of B. In other words, if you have two negatives, then the answer is going to end up being a positive number. This is another way of writing that. The second fact says, well, what if you have one negative and one positive? Or the reverse, a positive and a negative the other way. What happens when you multiply a positive and a negative number? Well, if you do that, then you multiply A times B. You actually get the opposite of the absolute value of A and B. Again, it's just telling you that if you have two numbers, one's positive, one's negative, then you will get a negative answer when you multiply them. This is another way of writing that. Now you've seen the properties of multiplication for whole numbers. The properties for integers are much the same. In fact, I don't think there's any of them that are any different actually on this particular one because we don't have the ability to do inverses because we don't have fractions still yet. Closure property says that if you multiply two numbers together that are integers, you get a unique integer. Right? Two integers multiplied give you another integer. Right? I can't do 5 times 3 and somehow I ended up with a fraction. Or 7 times 6 and I ended up with a square root. It doesn't happen. Integers multiply to give us other integers. The commutative property says that when I multiply A times B, it's the same as multiplying B times A. Associative, if I multiply A times B times C, it's the same as multiplying A times B times C. We regroup differently. I mentioned this before we started today, the identity property. The identity property says that there is a number that if you multiply by it, you don't change the value. And in fact, your last test we did that for whole numbers. That number is 1. So 1 is the unique multiplicative identity. Okay, so we call it a multiplicative identity. I'll write it here just so that you have it written down in your notes. Such that 1 times A equals A times 1, which is equal to A. The distributive property, there's two versions of this, and again, we've seen this happen before, A times B plus C, or you can write it as B plus C times A. So the multiplicative part, or the distributive part can become either before the addition or after the addition. And it would be the same AB plus AC. Here, if you want to keep the order the same, just to be aware of it, is your BA plus CA. You can distribute multiplication over addition. It works over subtraction as well. There's nothing special about addition here. You can put subtraction in there. And the last one is the zero multiplication property. And it says, of course, that 0 times any number, or any number times 0 equals what? 0. And it's the only number that happens with. So this 0 is unique. It's a unique number that does that. All right, so we're going to identify the properties that are present in the next 4 examples. -2 times -3. Remember that E says is an element of, and I is integers. So what property is present in -2 times 3 is an element of the integers? That's closure. It's just telling you get another integer. So this is the closure property. What's B? The zero property. How about C? That's the distributive property. How about D? And that one's commutative. This is old hat by now, right? No new properties even. Same ones we've done before, and they work the same way. There's a series of 3 different theorems. And These theorems talk about what happens when negatives are involved, because that's the new piece, if you will, of multiplication with integers, is there's negatives involved. So for every integer a, -1 times a is the same as negative a. When you have a negative a times b, it's the same thing as having negative times ab. Negative a times negative b is equal to a times b. For all integers a, b, and c, we have the distributive property with negatives. I mentioned that when we looked at the other one that it worked just fine for negatives, and now here's the theorem stating that fact for us. A times b minus c is ab minus ac. B minus c times a is ba minus ca. All right, let's run through this real quick. None of these are going to take too long. If it keep you over 2 minutes, are you guys going to survive okay? Is that right? Integer division. For all integers a and b, a divided by b is the unique integer c, if it exists, such that a is equal to bc. And you guys know that. You usually think about it being written as division like fraction division. A divided by b is equal to c, if and only if a is equal to b times c. Maybe you think of it in terms of cross multiplication. You can certainly think of it in terms of simply multiplying by the denominator, that kind of stuff, and we get the same thing. So again, we talked about this when we did this with whole numbers. The reason or the way that kids usually learn that 6 divided by 2 is equal to 3 is they ask themselves, what times 2 is equal to 3? Or what times 2 is equal to 6? And the answer is 3. So they rely back heavily on their multiplication facts in order to do the division. We've seen divisibility back in chapter 4. We saw it with whole numbers, but it works to be true as well with integers. If a divided by b is a unique integer, then we say that a is divisible by b, or equivalently, b divides a, and it's written with that notation we saw before with that vertical bar. B divides the value a. And the last pieces of information here revolve around inequalities. We saw inequalities happen again before with whole numbers. For all integers a and b, a is less than b, written with the symbols you're familiar with, if and only if there exists a positive integer k such that a plus k is equal to b. And again, if you think about it in terms of numbers, the reason that 2 is less than 5 is because there is a number I can write here that makes them equal. And in particular, with this example, it would be 3. There is a value that I can add to 2 and it will actually equal the larger value. You can also talk about the positive negativeness of subtracting values. For example, for integers a and b, a is less than b, or we could say b is greater than a. If and only if when you subtract the bigger one minus the smaller one, you end up with a positive number. So we'll use a positive and a negative. For instance, let's say we had -5, or we'll use 2 negatives, is less than -2. I could do whole numbers, but we've already seen that happen. So why is -5 less than -2? Well, because if I take the larger one, -2, and I subtract the smaller one, namely -5, I end up with a positive number. Right? Because minus the -5 would be positive, -2 plus 5 would then be 3. So anytime I take the value that's larger, whether it's a positive numbers or negative numbers, and I subtract the smaller one, I end up with something that's bigger than 0. All right, our last set right here, x is less than y, then x plus n is less than y plus n. We saw that happen before. If x is less than y, then negative x is greater than negative y. When we switch the signs, we make the signs negative, it switches the sign in the inequality as well. In general, if x is less than y and n is greater than 0, then nx is less than ny. But if the n is negative, then nx is greater than ny. Okay, so these two are almost identical. The first one that I put the arrow on basically is saying it's just -1. The last one is saying negative anything. And they're telling you that when you multiply by a negative number, the inequality signs switch. And if you use an example with numbers, you can see it pretty quickly. 1 is less than 2, but if I talk about -1 and -2, well, -1 is bigger than -2, right? Those are just concrete examples with numbers. The last bit here is about solving equations, some very basic solving equations bits. So if you were to do this, you can distribute, of course. This is simple pre-algebra stuff, actually. So you're hitting 6th or 7th grade, depending on your school districts and the ability levels of your students. So -5x plus 15 equals -5. So walk me through it. What would I do next? How about subtract a 15? You guys good with that? We will subtract 15 next. So -5x equals, what's -5 minus 15? -20. And then what would I do? I would divide by -5. And you would get 4. Good. And of course you can check to make sure it's right by plugging it back in. On this one over here, what I want you to recognize is we could go through some algebra to prove what this is going to be, but take a look at what's here. One says x minus 1 and the other one says 1 minus x. And actually, interestingly enough, Hannah's example is still on the board behind us, which is 3 minus 2 and 2 minus 3. What happens when you do 3 minus 2 and 2 minus 3? How are those numbers related? Okay, so they're additive inverses. In particular, they're the same number and opposite signs, right? So what we see happening here is that these are going to be exactly the same thing, except that one of them will be positive and the other one will be negative. But what will happen when we square them? They'll be exactly the same, no matter what x is, right? So this actually tells us that x is any number. And in particular, since we're working with integers, we'll say any integer. Any integer will have this property because the two pieces that are in the parentheses are exactly the same and only opposite signs. So when we square them, the opposite signs bit doesn't matter.